Yeah, we're quite constrained, so I'm going to quite rush through this for time. We're Aperture Labs, which any gamers in the room will know, possibly.
Yeah, we are not Aperture Laboratories, and that's important. We do occasionally get their mail. There'll be sandwiches though. So we do occasionally get their fan mail. Dear Aperture Laboratories, do you make portal guns? Do they work? Well, I have an idea for a portal gun. Here's the picture. The portal colors are yellow and rainbow, from Joshua.
Sadly, we had to say no.
Yeah, so stop making Major cry. I have to say with this picture, it's blatantly photoshopped, and I think of myself as a reasonably smart guy. I was really not thinking when I Google image searched for the word fist, just so you know. I really don't want to go there. So I'm Zach Franken. I tend to handle the hardware, which day job means doing things like etching chips down to the silicon and ripping apart any sort of hardware that claims to be secure.
Yeah, so if you try and implement stuff the way we were just talking about, then we'll drill into your chip without even talking.
Yeah, and it's amazing that happens quite a lot. So we were talking about PIC chips earlier. You can send a low-end PIC chip off to China, and you can get the code back for about £90. So it's that easy. More modern PIC chips, price goes up, but they'll still send you the code. So it all depends how much you want it. So this is Adam. He is Code Monkey.
So I take the nasty analog crap and turn it into proper.
Yes. So this is RFIDler. So we've been abusing RFID for many, many years. And as there's been a trend in software-defined radio, we wanted to create a software-defined RFID device. So there are devices similar to this. They tend to be very expensive, though. So there's a device called the Proxmark, which will do low frequency and high frequency. However, it clocks in about $300, and this should hopefully clock in about 50. So we're trying to kind of get the cost down, make it accessible to people, and also to allow people to realize that most of the Prox cards in your pocket are dreadful. There is no security. I mean, there is no security in many, many Prox cards. I could walk past you in the street, and if I have a reader in my pocket and it's turned on, it will just tell me your secret code.
How many people in the room actually use a card to get into their office?
Okay.
You probably find the manufacturers who install the system don't even know what.
Yes, and that's one of the things we definitely noticed that. So the installer that came and sold you the system initially will have gone to a distributor, and they'll have bought the reader and cards from the distributor, probably from a well-known vendor. But they actually don't understand how it works. They don't understand the protocol between the card and the reader, and they don't understand what's underpinning the security. So here is, do you have a head? Okay, so there's a card here made by a very modern manufacturer. I will not name them per se. I will use the nice blank one where the words hid are in very small letters. Okay, so very big manufacturer. Here's their access control card. There are two numbers on this card. One is 30115, and the other is a longer number. So this is, there are 24 bits of security on this card. and I've just told you 16 of them. So now you know that. Now you've seen my card. You now have a 1 in 256 chance of guessing the last number, which is the site code. Yeah, it's ridiculous. This card is very slutty. It will talk to anyone. It will literally, any reader, it will, you hold it up to any reader. Could be a reader in my pocket. It could be a reader in another building, and it will just tell you its secret code. Not great.
We've actually done it. We did at a conference, we put a reader under the table where you gather outside to get your coffee, and we put a camera on the wall behind it. And every time the reader tripped and read something, it took a picture and superimposed the ID on it. So afterwards, we had this little photo gallery of, here's the guy, here's his door.
So, yeah.
An hour later, the authenticator took that disk away from us.
Yeah. Yes, because a lot of the federal buildings in New York use cards like this, or Washington. Yeah, so there's lots of poor security here, and it's only by devices such as this that people get to play with it and go, well, actually, that's really bad. And no, you don't want to put one of those on the door. So hopefully, it'll help kind of open people's eyes to the scary truth. So, a whole bunch of standards. RFID, RF stands for radio frequency. However, most of these cards are not up in the radio frequency. They're actually inductively coupled. So there's a coil here, there's a coil in the card. It operates like a transformer. So you generally have to be quite up close and personal, but you can get long-range readers. They'll read from maybe a meter and a half away. Very good for coffee tables. So, so we started. This is version 1, which has a nice hand-etched board. So we tend to use PICs quite a lot, and we use this guy, which is a USB bit whacker. This is a bit whacker 32, so this has a PIC chip on it, simply as a handy platform for doing stuff with. So as we tend to use this as our kind of go-to platform, one of the things we said when we looked at this, we'd look at other platforms. So we looked at ARM, and we're scared away by the tool chain, basically. Because, again, we wanted it to be as accessible as possible. So the whole idea is to provide this assembled, but also as a bare board for people to assemble themselves, and also kind of dual use. So it can be used as a platform for looking at cards and playing around, but you may have your own open source project that you want to embed it into. So you can effectively have the bottom part of the board, which is the reader circuit, and keep the top end, which is the CPU, kind of separate, basically. So, sorry, do you want to talk about everything else in software?
Okay, so yeah, so the whole premise of this was that with all these different designs and different standards, there are circuits being designed to cope with each different standard. So I've actually got some more detailed slides after your next pictures, but the whole idea of this was we have the nasty, scary analog circuit down here, which is the bit he's good at, and then we have the lovely, shiny digital circuit up here, which is the bit I'm good at, and we get them to talk to each other. So all I get is the digital output that we can then process and decide in software. So we ignore whatever the standard is. All these different tags have different standards, but I'll talk in a minute about why fundamentally they're all talking the same language, even though they're very different. So I don't know if we want to.
So yes, so that's a quick pick of the.
So that's the actual just the bit whacker.
Which is this nice little red board. They're about 30 quid, I think, and make a nice little development platform.
It's a really nice board, actually. I mean, it's a PIC 32 with all the pins broken out and USB stack and everything, so you just plug it in. And as I said, we start a lot of projects with an off-the-shelf one of these and just plug peripherals into it. So,
could you put it through it on a simple serial?
Yes, I mean, it's got hardware and software UART support on it. So, and in fact, RFIDler comes with a USB port, but it also comes with, I mean, I'll do a demo. Basically, there's a menu system, and it auto detects if you're talking over serial USB or serial UART. So you'll flip between the two.
So that's the board I was just waving around. If it comes back again, there we go. And it's going to disappear again. So, as I said, try to split it between the kind of analog and front-end processing and the CPU back end. And it's really a reasonably simple device. We have a detector here, which is, so hands up, who knows how this type of RFID actually works? Okay, right. So simply, you have two coils, one in the reader and one in the card, and they are resonant circuits. So they normally resonate at about 125 kilohertz. So this has an oscillator attached to it. It's resonating at 125 kilohertz. And this has a resonant circuit, which is a coil and a capacitor tuned to that same resonant frequency. So when you hold them close together, power gets transferred across, and this is what powers your card. In order for the card to signal back, what the card does is it shorts out its own coil. It's kind of like plugging its fingers in its ears or choking off its own air supply. But when it does that, it causes a very small voltage drop in the energizing coil, like 100 millivolts or something like that. And that's how it sends back a bit. So this card here, which is a 26-bit card, has 2 parity bits and 24 bits of data. In order to get that data across this air interface, it sends about 540 bits to get those 26 bits across. So this is what our very front-end circuit is doing. It's detecting that small voltage drop. We then have some comparators for threshold detection, and then we simply take it through a Schmidt trigger and an OR gate. We also use a digital pot to set the thresholds on these comparators. And the main reason for that is we want it to be software controlled. You've noticed this has a couple of small trimmer pots on it. That's for when you are deploying it as an actual device. You don't have your CPU. You're not using the digital pot, so you can actually set it to something sensible to read the types of cards you want to use.
Yes. Can you explain why it is you need 540 bits to transfer 26 bits?
Because a lot of them get dropped. It is error correction, effectively, yeah. So this layout looks absolutely terrible. That doesn't look much better. However, one of the things we wanted to do was to make it possible to hand assemble. And it's a little bit tough with a chip of this density. But hey, so I spent ages trying to work out why I was having issues, because I thought, well, if someone gets a light version, wants to drop a CPU on later, if I make all the pinouts identical to the bit whacker, then they can just drop a bit whacker in. The pitch on the chip on the bit whacker is a lot smaller than the pitch on this chip. And that would be absolutely impossible to do. And this is actually quite doable, believe it or not. All you need is a lot of flux. Flux is your friend.
Yeah, so he has actually hand-assembled these.
So.
Any bit that was manufactured is the
And not as evil as you think. So a lot of the main challenges were in the analog front end, because it's not just a reader, it's an emulator as well. It's also a sniffer. So the trick was integrating a lot of this stuff without messing up our analog signal. And again, trying to kind of lay everything out to make sure everything has reasonable spacing. It's not actually very tight when you don't have your headers in place. It's all nice and flat, gives you lots of access to solder things like the large PIC chip here. And again, we've tried to avoid small chips like this. However, some were unavoidable, but these have the same or larger pitch than the PIC.
This actually is a completely open design. You will be able to download the drivers and everything and just build it yourself.
And of course, one of the last things when we're just talking with the hardware is to try and get the bill of materials right. I'm shooting for about £15 all in. I don't know if I'm going to make it yet, but that's what we're aiming for. So if you're buying these PIC chips in the 1,000, I think we managed to get the price down to about £5. So, and as it's a top-end 32-bit PIC chip with, I think, 512 meg of flash and 120K of RAM, it's quite beefy. Onboard Ethernet controller as well, I believe, on that one. So it's come together quite well. As I said, trying to control the cost of the BOM is a nightmare, because every time you make a change, we've then got to build a board and test it to make sure that just because we went with a cheaper component, we're not killing things going forward. So I'll pass you on to Adam now, who's going to do a bit of yeah.
Okay, so this was all inspired by software-defined radio. So I'm going to go quite quickly through these so I actually get to the point I can do a demo. But basically, if you're into software-defined radio, there's a very cheap dongle called the FunCube, which is actually a partner to a satellite. So there's a satellite flying around which is transmitting, and you can get this dongle and receive radio stuff with it. So it works with GNU Radio, which is an open source software-defined radio stack. And basically, if we look at something like some raw audio coming in, or some raw data, and we save it as an audio file, a WAV file, and then look at it in a WAV editor, it'll look something like this. So we got bursts of data, and there's obvious, just very fixed data. So if we zoom in on that, what we can actually see in this case is some big pulses and some little pulses. And this is what we call ASK, or on-off keying. So it's either on, talking, or it's off, not talking. Yeah? And this is AM, amplitude modulation. So either you've got signal or you haven't got signal. Yeah? So we quickly ran it through a GNU Radio transformer, and that will convert it into, so it demodulates the AM for us, and we now get something that starts to look more like a data stream. So we've got highs and lows. It's all a bit raggedy, but again, very easy to process. That's a WAV file, so you can just write a bit of Python or whatever that tidies it up. So turn it into a nice square wave, and now you can start to see that if we take the highs as a 1 and the lows as a 0, you can actually turn that into binary. So I've now got 1011, 011. So I'm happy, because I've come out of the horrible, scary analog world, and I'm dealing with real ones and noughts. So I can understand that. RFID works exactly the same way. You've got your carrier, and that's used to energize the coil, as Zach explained. when the tag is talking to the reader, it's grounding its coil and causing a fluctuation in the signal on the coil. The reader can detect that because they're coupled together. That's going to affect the reader's coil as well as the tag's coil. So he can see those pulses. Yeah? When the reader wants to talk to the tag, it actually shuts the carrier down altogether, so it just stops talking. So there's a brief gap in the signal that's going to the tag, and the tag can detect that because it's lost power. So it detects the loss of power and it measures the gap, or it measures these bursts between the gaps, and thereby knows whether it's a 1 or a 0 that's being sent. Now it doesn't power off long enough for the tag to die, because it's storing some power, so it can survive through that little gap. But that's how they talk to each other. Is this making sense? Ask questions as we go along rather than wait till the end.
Can I just mention that a lot of tags don't actually have a conversation. So ideally, we'd like a security model like we saw with Chris, where there's a conversation, a key exchange, and your secrets go across like that. Quite often, the reader isn't talking to the tag at all, it's just energizing it, and it's only the tag that does the talking. But there are tags that take that bidirectional communication.
Yeah. Okay, so the basics are the same. We're talking either on or off. So we've got ASK, on or off keying. And that's the only modulation scheme there is in RFID. So what confused us at first is, what are all these other modulation schemes? Why is this stopped? That slide not coming up. Don't you love it when a plan comes together? Sorry about this. I don't know why I can't start from there, but apparently I can't. I need a Raspberry Pi to run my slides on.
There we go.
Okay, so interestingly, it's my screen has stopped at this point, but that's okay. So there are these other schemes: pulse width modulation, FSK, Manchester, and so on. So what's going on there? Well, if we look at the details, this is the signal you'll see. So ASK we've talked about. You're either damped or you're not damped, and a bit hard to see, but we've got the up and down signals. So ones and noughts.
Yeah, but how do you know it's not doing alternate mark inversion, so you have voltages? So you've got your ones and noughts, you've still got to know what the brakes colours are.
Yes, you do. I mean, you have to, you don't know for sure. And actually, when I do the demo, you'll see that you have to start to do some thinking to figure out what's going on. I mean, ASK, if they're doing Manchester encoding, this is a very handy protocol because it's self-correcting, it's error-correcting. You can actually tell. So instead of a bit period, a 1 just being all on or all off, it actually changes halfway through. And what that means is that your 110110, you actually take 2 bits at a time, and it can either be 10, which equals a 1, or 01, which equals a 0, but a 11 is invalid. So in this case, if you just drop into the raw bit stream, you've got bits coming through 10, 10, 111. You don't know if you started at the beginning or midway through the stream. In this case, the first 2 bits are invalid. So we know we're half a bit off. If we throw away that first bit and start here, from then on, it will be correct. So we've auto, well, if it isn't, it's an error. But we've auto-corrected. We've now got our clock synchronized with the sending clock because we know that's the start of a bit and not that. So that's half a bit out, yeah? And I'll show you that in the demo, which actually I'm going to skip all of this and go straight to the demo, or we're not going to get a demo. I can get out of here. Oh, you vicious bastard. Come on, let me out. So the board has a USB interface by default, which get that lined up somewhere. So we had terrible problems with the resolution of this screen. I can't believe it. Oh, there we go. Is it too high or too low? Okay.
Drag it over a little bit if you can, to the right.
I can't.
You sit down on the seat and just put the,
Sorry,
put it on the edge so you can see that screen.
yeah, the trouble is you're not going to be able to see the edge of my input.
No, that's what I'm saying, rather than using that. Sit on the edge, turn that round, and look at that screen, rather than this
Yes,
screen.
but the data's here.
Can you just drag it that way a little bit?
Use your imagination.
Yes. Some really great stuff is happening here, apart from the blinking lights.
Okay, I'm going to start with another screen.
There we go.
There we go. No, this is the problem. We had loads of problems with the screen resolution. For some reason, I'm detecting that as a 640 by 480. So it's being weird. Okay, so if I go... Okay, so, oh, this is a bloody nightmare. I can't see that at all. So he's gone off the bottom of the screen. Sorry, this is...
Shrink the terminal down as well.
There we go.
There we go.
Okay. Hurrah. Okay, so we can do multiple things. So basically all these tags are basically talking the same underlying protocol. It's ASK. So if I have a look at this guy, this is actually a tag called a unique. So if I, within Fiddler, we've tried to make this as simple as possible, so you can actually just say stuff like, okay, set this, set tag unique, and that's now configured to be a unique. It sets some underlying things like that's gone off the top of the screen. Here we go. So data rate layer above. But if I ask it what's its UID, that's the magic number. So that's the code for this particular card. But we've decoded that from raw data. So if I was to say set tag to ASK raw and get the UID, we get a much bigger number. That's just a raw stream of bits. And in fact, the fact that it says 555 and AA tells us that it's probably Manchester encoded data, because 5 is 1010 and A, or the other way around, A is 1010 and 5 is 0101. So we know that we're getting a Manchester stream. So you can use this to just look at any raw data and start to build up a picture of what the tag's doing underneath. And I mean, obviously I'm running out of time, but what I'll do is we'll stick around afterwards. Anyone who's interested in looking at this in more detail, we'll do a demo outside and you can actually go through all the different systems on the screen where I can see what's going on. But for example, one of the things we've implemented is, so if I read the tag, this is coming up as 11. Okay, it's not a unique, it's an EM. So set tag EM4X02, which is a different standard but happens to use the same underlying bit patterns. So the number there matches the number here, which is 11008F0D4A. What I can also do is tell this to emulate that. So if I say emu and that number, and I fire up my reader, stick it on the coil, probably too close. I've got another tag in my hand.
Is this Paddy? Adam?
No. Okay, well, the gods of the demos are against me, but you get the picture. Right. So everything's going wrong today. But so you can read, write, emulate. You can even clone to another type of tag. There are tags that can behave as different tags. So if I say, can you find me a Q5 in there? If I say copy to Q5, put the tag on the coil.
Okay, so one of these is most likely to be a Q5. Sorry?
Sorry, these, they're a fiver. So this is a blank tag that can be configured to pretend to be other tags. It's fully reconfigurable. So what I've done is said copy to a Q5. It's set up a virtual tag in memory, which is now pretending to be an EM. So it's a Q5 emulating an EM4X02 with that UID. And this is the raw data you would have to write to a Q5 to make that happen. So if I now put that on the coil and say clone, that's now written the Q5. And the Q5 is now the same as the original unique. So something worked. So yeah, we could walk, just down the rows, scanning your pockets and go, okay, that's the number, type it in, bing. Yes.
But sorry, can I?
No, I was just going to ask, it's quite concerning. I mean, do they really design these things to be breakable? So that people like CMFBR can just get in there and
I'm not sure they designed them to be breakable, but a big part of my talk, which we had to try and squeeze down, was why we've ended up in this situation. And the reason is partly because this is really old technology. I mean, these cards have been around for over 20 years. So the chips that used to have to read them were really feeble. But they're, it's one of those, if it ain't broke, don't fix it type things.
And in fact,
Well, that too, yeah.
And in fact, the data format that's on a lot of these cards comes from an original swipe type card called a Wigand card, which is even older.
Yeah, it's all done in hardware, basically.
Yeah,
So.
and it was Wigan cards had tiny little bits of paramagnetic wire in them, and literally in 2 rows. So you could hold a Wigan card up to the light, and you can read the bit stream of one. If it's on the top, it's a 0. If it's on the bottom, it's a 1. So that technology, they've just changed the delivery. That Wigan code, the 26 bits with which is 24 bits with a parity at either end, that has just gone to a different format. The hardware wiring that comes out of the back of the reader uses the same Wigan style signaling, which is 2 lines. You get a dip on one for a 1 and a dip on the other for a 0. No encryption. Even if you have a high security reader, you've still got plain text coming out the back. So when you actually delve into this stuff, it really makes you want to cry.
How much longer have we got for questions, or are we?
Well, I think what we're going to do is Aaron needs 5 minutes to set up, so we've got 5 minutes of questions while he's setting up.
Perfect.
Right, so questions.
Questions.
Oh, lots of them.
Yeah.
Over and back.
Two really quick questions. First one is with regards to the capabilities of the software. So for cards like micro, where you can mock certain segments, if I remember correctly,
Yeah.
can you clone those cards outright, or do you have to brute force them?
Um,
Code and then clone them, or?
Okay, this particular device is low frequency only, but when we move to the high frequency version, then you would be able to implement in software some of the MyFair attacks. So you'd be able to do a dark side attack, or one of the ones that actually recovers the key through parity errors on challenges. Yeah. So there's a high frequency version. As soon as we got this one out, we're going to start work on the high frequency version.
Quick question is about hardware. You can get really easier to solder than TQFP PIC32. Is there any particular reason you went for TQFP, and why not the shrink outline or maybe a heat?
Because he wanted something that was ridiculously powerful. Basically, he's the software guy, I'm the hardware guy. And I just get this constant nipping. Oh, I want more memory. Can it be faster? Blah, 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 blah. It's like, okay.
And yes, it can, PIC32. So.
It doesn't get any faster than this. You've got all the memory you need.
And it is fantastic from the software point of view. As you can see, it's quite verbose. It's got big menus. It does all sorts of stuff. And I've only used 30% of the code space so far. So. Yes, and actually you can. Yeah.
We have a question in the middle.
Yeah.
Out of curiosity, how secure are the Oyster cards?
Oyster card is using a MyFair, so the current generation. Yes, it can. Each card has a unique key for each block. So there's different blocks on the card, but the card is diversified. So there's a master key, and what they do is they diversify your card key by taking the master key and encrypting your unique ID for your card to create a unique key for your card, but not just for your card. There's a different one for every block on your card.
Yeah, so they're encrypting the unique ID and the block number, and all of a sudden you have a unique key for that block.
But so it does mean that we can clone. We could go from here. I've got Kit with me. We could go to the reader in the station, sniff the transaction between the reader and the card, and recover your keys. And with those keys, or we can do an offline attack which takes longer. Yes, it's a symmetric key. And we can do an offline attack which takes longer. We could then clone your card. And so you put 50 quid on it, we clone it, we put it to one side, you use your card up, you then take the clone and start using that. You will be caught because they actually monitor the known sold value to your card and the value that the card presents at the machine. So
they do a reconciliation.
Yeah.
Transaction. Yeah.
If they see you coming through, they will try and catch you. So.
And do the reconciliations every night?
Yeah.
Yeah,
So.
Oh yeah, I mean, potentially buses certainly are fair game.
Yeah, you can use it all day for one day. But, you know.
Could you? Sorry. Two questions. Could you create new cards, like cards with IDs that were previously unknown?
If you use the master key.
So yes, so potentially if you knew the master key, and also depending on whether they were loading the cards onto their system as a batch when they purchased them from the manufacturer. So quite often they'll purchase a batch of cards. When the cards arrive, there'll be a disc with the cards that has all the serial numbers and any data that they need, like transport keys, etc., to access those cards.
Because it would be quite interesting to kind of, well, I mean, if you don't want to steal money from the system, but you want to anonymize yourself.
Why not just
So
steal
like
money?
create new cards every
Why
time.
not just clone the one in the bank card? Why waste time with the oyster? Just steal the money.